All right. So, chapter 10 is on gases and like gas properties and gas laws and stuff like that. So, and we've already talked about the 10.1 and 10.2. So 10.3 starts with actually some of the application, the gas laws. Okay. Now, the reason that I gave you guys both 10.4 and 10.3 together is me personally, I like to be efficient and as much as possible make things as easy as possible. So in 10.3, they give us like three different gas laws and relationships. But really, I am gonna walk through them with you and just kind of explain the relationship concepts. But in terms of the actual equation, when we get to 10.4, that's the equation we're going to use. Um, so to me, it's better to kind of know one equation and how to use it than it is to have to memorize three separate ones. You can use the one equation to get all of these. Okay. And it'll make sense more when we get there. But all right. So some of the variables we're dealing with here are temperature, pressure, volume, N. N is number of moles. Um, so the first one here, Boyle's law. Boyle's law says the volume of a fixed quantity of gas at constant temperature is inversely proportional to its pressure. All right, so inversely proportional. I know some of you guys have dealt with stuff like that in math. Um, Essentially,
you think I remember this?
Inversely proportional. It basically means that whatever happens to one thing, the opposite happens to the other. So if one variable goes up, the other one goes down. Okay. What that looks like in terms of a equation problem is like this, where you like P1 times V1 equals P2 times V2. So inversely proportional, you multiply them. Okay. Now, what this means is if the volume goes up, the pressure goes down. The volume goes down, the pressure goes up. Okay. Just to give you guys a sort of quick visual example of this. So if we have a bag here with a little bit of gas in it, I don't know if that was enough. Okay. So we have this. If we were to reduce the volume by squeezing it, we reduce the volume. What happens to the pressure? It increases, right? So that's basically this idea. If the temperature and the number of moles, which is like the amount of the gas you have, stay the same, if you decrease the volume, pressure will increase. If you increase the volume, pressure decreases. Make sense? All right. That's true. All right. So, okay. So you're talking about your lungs are an example of Boyle's law, the differential in pressure and stuff like that. Okay. Let's go to Charles' law. So Charles' law, the volume of a fixed quantity of gas, that means the number of moles doesn't change, at constant pressure, meaning the pressure stays the same, is directly proportional to its absolute temperature. What this means is directly proportional means whatever happens to one of them, the same thing happens to the other. So if the temperature goes up, the volume goes up. Temperature goes down, the volume goes down. Okay? This is shown as being divided, like one of them divided by the other when they're directly proportional. So we get V1 over T1 equals V2 over T2. All right. One thing to note, and I think I have this written on the 10.4 as well, but you have to do all temperature for these problems has to be in Kelvin. You will not get the right answer unless you put it in Kelvin. Okay. The top one would be the conversion into Kelvin. So you take the degrees Celsius. God bless.
Did you mess up again?
Mm-hmm. Luckily, this is an easy fix. There we go. Sorry. Degrees Celsius plus 273. Okay. To get to Kelvin, because Kelvin doesn't have any negative. The lowest you can be in Kelvin is 0. So if you have something that's a negative, you know it's wrong for sure in Kelvin. Okay. These all have to be in Kelvin temperatures. So so that's Charles' law. They use the hot air balloon example, which is actually a pretty good one. Like as you heat the air in the hot air balloon, the amount of air in the balloon actually doesn't change. As the temperature heats up, the volume expands, which causes the balloon to fill up. It also changes the density, which is why it floats. But that's the relationship between temperature and volume. Okay. Questions on that? All right. Last one. Avogadro's law. So they've got this like Gay-Lussac's law of combining volumes, which we don't really use very much. At a given temperature and pressure, the volumes of gases that react with one another are ratios of small whole numbers. Blah blah blah. Like basically, what that says is what that sort of leads into is this. Avogadro's hypothesis is that equal volumes of gases at the same temperature and pressure contain the same number of molecules, which is sort of weird at first. Like the idea that it doesn't really matter what gas it is. If you've got two gases that are in the same volume, that are at the same temperature and pressure, you'll have the same number of molecules. It doesn't matter what the gas is. So it's a little weird at first, but it sort of makes sense when you kind of think about like what pressure is, which is like the molecule striking the walls of the container, how often and at what speeds. And if that's all the same, then theoretically it means you have the same number of molecules inside the container. So this law is seen in the relationship between volume and number of moles. So it's directly proportional. V1 over N1 equals V2 over T2. So if the number of moles goes up, the volume goes up. If the number of moles goes down, the volume goes down. If the temperature and pressure stay the same. Okay? All right. This last thing, we can show that 22.4 liters of any gas at 0 degrees Celsius, 1 atmosphere contains 6.02 times 10 to the 23rd gas molecules. So this gives us the conversion. Essentially, 1 mole of a gas is always equal to 22.4 liters of that gas. So you can convert between volume and moles, which isn't something we're used to doing. Okay. That's just for gases, though. All right. Any questions on that?